which is basically can be formed due to the mechanical deformation or a thermal. So those both can be play an important role to the formation of residual stresses. So what residual stresses harm to the material, because it's basically stresses also already induced strain in your material you already have. So whenever you are going to deform it, or you are going to put some extra pressure on your material, the earlier stress or strain whatever you had in your material is going to affect the overall property of your material. So the residual stresses basically play an important role at the fatigue life or a mechanical behavior of your material. And the second part is anisotropy on our major issue in additive manufacturing material. So what anisotropy? Because when you are talking about the build direction, or there is another transfer direction is there. So in both the direction, the growth mechanism is going to be different. That growth mechanism is basically trying or basically form the heterogeneity in your material. So if you say the defect density in build direction is going to be different, and the defect density in the other direction is going to be different in additive manufactured material. So other than these type of problems, then there is a texture difference is also going to be observed in additive manufacturing material. These are the electron backscattered images. As you can see, these are the electron backscattered effect images. What is electron backscattered is basically EBSD. So which basically tell you about the like how the grain inside your material is going to be oriented and how it is going to be look like. So if you see, these are the plastic strains or residual strain which are observed. You can see these are the formation. If it is like a homogeneous or a like material is fully recrystallized, then it should showing a single grain color. Like let's suppose it's a particular grain orientation is there 111 or 100, so it's showing it should be in the single color. But now you can see there are some strains are available in the material. So these type of stresses basically later on move towards a residual strain in your material or residual stresses in your material. And these are the columnar epitaxial columnar morphology is directly observed. These epitaxial growth is basically moved towards anisotropy in your additive manufacturing material. And if we'll talk about how it is going to be different, let's suppose you made a material of which is having a height of around to be 40 mm. So in this current paper, what they observe, they find out the thermal gradient is basically playing an important role. So how the thermal gradient is there? First, they observed. They also calculated the texture in your in the material. It's at height of 0.5 mm. When they are moving towards the build height of around to be 35 mm, you can see at around to be 25 mm. It's a pure cubic texture is available in your material. So this is the pole figure, which basically representation of your texture, the 3D in the two-dimensional texture. So you can see the presence of cube texture is directly visible in your material. So these are the anisotropies which basically we deal during the whenever we are going to perform any additive manufacturing material. So this is again one two of the good papers in good journals. So which they also talk about the growth direction, and which is basically depend on the location dependent fracture toughness they calculated. So but and other than that, they saw the microstructure variation along the build direction. So if you can see, there are so many like presence of stresses is there, or misorientations are there. In terms of EBSD, you can see these are the misorientation which you can see inside a particular grain. So there are so many misorientations available inside the grains. But if we'll talk about another direction of your material, build direction, the material is totally recrystallized. It's look like a totally recrystallized material. But aspect of that or contradictory of that, you can see there are so many the misorientation presence inside your material. So this is basically the how the power and the build height is basically changing the material morphology. So they also did the with the help of X-ray tomography to find out how the defect volume is going to be changed throughout the build direction. So what they observe when we are talking about the defect volume, around to be it's going to be more in opposite of the build direction, because of the diffusion kinetics is basically changing in that particular direction, and they see the formation of cracks which is directly observed, and this basically confirmed with the help of X-ray tomography. So these are the heterogeneity which we most of the time faces in additive manufactured material. So how these are going to be changed, or what are the various problems we face. One is the scans, how the scan rate is going to change the porosity of your material. In this, they basically try to simulate that problem with the help of different in software. So what they observe in build direction, they are talking about more columnar growth of structure. But if we'll talk about in the jet direction, like it's basically jet direction is basic build direction, so columnar growth is observed. But if we'll talk about in XY plane or 2D plane, the fine grains were observed. The same schematic or the same observation they observed when they are performing it with the help they are doing it with the help of microstructure analysis. So a one effect of various scan strategies on porosity, which basically not much explored yet, and how this resources generation is going to be taken place. This is going to be an important part of that. So they also did some atom probe tomography. This is also the formation of some defect structures are also visible, and some also presented the formation of hydrogen generation in the material. So through that, I'm going to show you the first paper. This is basically as built and post-treated microstructure of electron beam melting, which is basically produced by nickel-based superalloy. As nickel-based superalloy is material which is used for uh, aerospace application. So because it's having good high temperature properties, so creep and those behaviors of the material is quite good. So these are basically used for aerospace applications. So in this part, we basically talk about two different samples. One is in a contour direction, another is in a hedge direction, to see how the variation is going to be occur. And then those two samples are one is as built, whatever we produced with the help of electron beam welding, and then electron beam, then additive manufacturing. Then second is the hip is basically hot isostatic pressure, because it's a high temperature deformation. So it's a thermomechanical processing is we performed on those materials. Then hip plus heat treated, mean to say in this we are basically talking about because you are basically deforming at high temperature, so some of the deformations are already present in your material. So to remove those deformation or misorientation or residual stresses, we performed some heat treatment on those samples. So this is basically schematic of that. These are the different samples which talk about hitch and contour direction, and this is basically build direction which we see already seen in your. So we took samples from the contour as well as the hedge direction also. So, so first, when we got this material, we thought of let's see the microstructure of the material with the help of SEM, scanning electron microscopy. So the grain structure, if you can see in contour in contour direction you can see there is a small amount of columnar growth, and there are some fine structures or some fine grain structure is also visible. But when we are moving from contour to H, the formation of fine grain structure is more. In H direction, it's a purely fine grain structure is observed. But in the contrary, in contour direction, the presence of larger grain or columnar grains are also observed. But if we'll talk about in bill direction, like it's basically taken on the surface. Now we are talking about the bill direction, how the bill directions look alike. So you can see there are some talking about this, there are some cracks or cracks are already observed, and there are presence like this you can see these are the cracks, or you can see the growth is not taking place in a proper way. And then if we'll talk about in the H direction, this is totally a columnar growth is observed. So, but when we are talking about contour to H direction transition, you can observe the columnar growth, and there are some amount of larger grain structure is also observed. So we thought of, let's see the EBSG of those things, because EBSG will more focus on the texture of your material. So texture I already explained. It's a basically orientation of your grain, how your grain is going to be look like, or if we'll talk about how it is going to affect, it is going to affect your mechanical behavior of your material. Let's talk about it more common way. The material like iron is whenever we are going to use sheet metal formation in iron case especially, we try to capture the gamma fiber of your material. So gamma fiber is basically 111 orientation of grain, mean to say if we'll talk about in layman term, the more blue grains type of structure in your material. So those is basically it's basically anisotropy of your material, like mean to say your material is going to be oriented in one single direction. So to see this, how this is going to be observed in because we see there are some fine grain structure is there. So is it true with we just want to see with the help of EBSD. So there also we see in the build direction there are some fine grain structure is there available at the corner of our sample. So but if we'll talk about in H direction, this is again as observed earlier, this is going to be columnar growth. So the same structure we observed in this. So these are the columnar growth structure is there. Parallelly, we are getting some low angle grain boundary. So low angle grain boundary mean to say uh, is basically misoriented in misorientation is there. So grain boundary is mostly either tilt or twist. So those type of structure is basically observed in H direction. So how the because if we talk about nickel 718 as told earlier, there are n number of precipitates can be observed. One is basically the presence of because niobium is there, so there are different type of carbides can present. Other than that, there are gamma prime, gamma double prime, and delta phases also can be present in your material. So to confirm, are the precipitates are going to be changed if you are changing from contour to H direction, or in itself in the H direction. So or there is a, because there is a transition is there contour to H. So are the presence of precipitates are going to be changed or not, or the volume fraction or a weight fraction of that precipitate is going to be changed or not, that are also we are trying to observe. So first we with the help of again the scanning electron microscopy, we observe there are some different type of different shape and size of precipitates are present. So what type what those precipitates are? So To confirm that phases, we did some elemental analysis of those phases on those precipitates. So what we observe, there is a presence of gamma matrix, mean to say your material, which is basically nickel dominated, and again nickel dominated with the iron and chromium. But there are some fine precipitates are there, which is basically more focused towards the niobium carbides. So the presence, like earlier, the in the matrix we basically observe the nickel percentage is around to be 52% or 53%. But when we talk about the precipitates, nickel percentage go down and the niobium just shoot up. So from 4% to 25.8%, like around to be 26%, the presence of niobium is there. So it's basically niobium carbide, which is forming near to the grain boundaries or inside a grain also. So it's a basically composite kind of, it's a matrix with the nickel base, and if we'll talk about precipitates, it's basically niobium carbides. So are these basically presence in the build direction also? So we try to correlate that part. So what we observe, there are different type of phases are present, or different type of precipitates are observed. So if you can see, there are n number of precipitates are there. So all those are basically talking about delta phase. So it's basically intergranular delta phase are present, or there are parallelly some networks of delta phases are there. So these phases or these precipitates are basically later on going to affect the mechanical behavior of your material. So to find out how the defect, because as already discussed earlier, in the additive manufacturing, defect density or a defect fraction is also going to affect your material. So to confirm that part, we try to take two different samples, one contour one and the H one, and try to find out how the defect fraction is going to be. So then we calculated it. So in build as build sample, because it's as a build sample, so defect fraction or defect volume fraction is too high. It's around to be around 40 to 43%. So in both in contour as well as in H sample. But when we applied hip, the uh, defect fractions go down, and then hip plus heated, it's again the defect fractions go down. So now whatever sample we are like after heat treated, because heat treatment is basically because now we are giving there are two types of deformation. One is the mechanical deformation, other we can give thermomechanical, mean to say thermal plus mechanical deformation. So in hip basically we are talking about thermal plus mechanical, because we are heating it and giving some deformation. In hip plus heat treated, mean to say after hip samples we basically heat it at particular temperature and hold it at and then cool it. So the here again during cooling there are chances of more the presence of more precipitates will be there, because in nickel based superalloys at about 900 degrees Celsius the presence of precipitates is going to be changed at that particular temperature. So to so we can see in as built there are so many defects fraction will be there. So to overcome that, we heat the material, we give some thermomechanical deformation, thermomechanical plus heat treatment also given to that, to remove the anisotropy of your material. So again we did some microstructure analysis of that. These are the scanning electron micrographs. So we can see there are the formation of twins is there in contour part, in contour. And when we are talking about hip plus heat treated, so after heat treatment there are some twins fraction is go down. Twins is basically spatial grain boundary fraction is go down. So and hip in this direction, when we are talking about, these are only the contour direction, but when we are talking about H direction, there are after hip plus heat treated and build direction, as already shown, there are fraction of some fine grains are there. But if we'll talk about in other direction, build direction, these are columnar growth structure is there. And after hit plus hit rated also, the columnar growth structure is there, but the grain boundaries or the number of grains is go increase in one particular direction. So then again, how the uh, texture is basically is going to be changed. To find out that, we did some electron EBSG on those samples. So what we observe when we are talking about hip plus hit rated sample, because in earlier also, like normal sample without hip or hit rated as well as samples, there are textured variation was there. The same after heat treatment also we observe there are the in H direction as well as in the contour, there are mostly like number of grains, like grain size is quite big, but the texture is no, texture is not homogeneous, or we can say it's a random kind of texture is there. But if we'll talk about in heat plus heat treated in H direction, there is single texture material is highly textured and mostly oriented in 100 direction. So anisotropy you can see in H direction because of the texture presence. So so after this, we thought of let's do the EBSD in the build direction and see through all the samples. And because earlier all the samples are performed on like small area. So because we prepared a material which is having around to be 4 mm of dia, so we thought of let's do the capture the whole area, how the structure or microstructure is going to be changed throughout your material. So to do that, we did the EBSG analysis on throughout those samples. So what we observed in as build direction, these are basically H samples only. So in as build direction, there are a columnar structure, and at the corners there are some fine grain structure is also there. But when we are basically deforming it through thermomechanical processing, so there are presence of some misorientations are there. So these are basically one of the reason why or we can say these are the presence of because of the deformation, there are presence of residual stresses or residual strain inside your material. And then this is, you can see these are the unindexed point also. These black points are the points which basically you couldn't identify with the help of EBSD, because either they are highly disordered or because of the polishing problems. So, but if we'll talk about hip plus heat treated, the same deformation which we observed or same misorientation which we observed after in hip samples are now is totally removed with the help of this heat treatment. So to confirm that, we also calculated the CAM. CAM is basically kernel average misorientation. Kernel average misorientation means to say, like, let's suppose you have a grain inside your material. So this what is going to it's a basically grain inside your material. First, we are going to calculate the misorientation in your particular grain itself. It will come out as to be as an kernel average misorientation is basically, let's suppose you have a grain of around to be 250 pixels. So if we'll talk about the single pixel is going to check the misorientation or orientation with respect to neighbor of its five orientations. So let's suppose this is our pixel. So this pixel is going to check the misorientation near of its neighbor of its 5 pixels, and then according to that it is going to identify as one misorientation in your sample. So if you can see, there are some misorientation are there inside your material. So this is the best way to find out how much misorientation is there, and with the help of that we later on also calculate with the dislocation density inside your material. So to confirm this part, we also calculate grain average misorientation of your material. Grain average misorientation on those all the same samples is basically first calculate the misorientation in one grain and then take out the average of that part and then compare it with the each pixel of your grain. It if I can explain it in more precise way or more uh, layman term way, let's suppose you have a grain which is basically uh, mixture or basically addition of 1000 pixel inside your grain. So first in this calculation what we did, we calculate the misorientation of 1000 pixel and then the take out the average of that 1000 pixel and then compare that average with each pixel. So this will give you the more precise answer how the misorientation is present inside your material. So if you can see in the same samples, you can see there are misorientation is there in a particular grain. So here it is confirmed how much misorientation is there, and this is after heat treatment. These misorientation are easily removed. So this again proved that after heat treatment there are after thermomechanical deformation there are some residual strain or residual stresses are present inside the material which easily removed with the help of heat treatment at a higher temperature. So this again the Gauss grain orientation spread which talk about how your or grain is basically oriented in different directions. So this is basically grain orientation spread. So to confirm that part or after throughout this whole terminology, we want to find out how the precipitates are there and how can we calculate the volume fraction of niobium precipitates, or is there the volume fraction is going to be changed when we are moving towards the contour to H direction, or how those fraction is going to be changed when we are heat treated the sample. So first we can see there how many precipitates are there in build direction. So what we observed in contour direction, there is precipitates are there, but the size of the precipitates are very small, which is talking about less than 1 micron. But when we are talking about hip after hip sample, the precipitate fractions go up. In the contour direction, hip plus heat treated, again after heat treatment the precipitate fraction go up, as I told you, because we are giving the heat treatment above 900 degrees Celsius. So there is the chances of gamma double prime precipitation of gamma double prime would be possible. So these confirm that part. So this again we also try to calculate it in the H direction also. So in H direction, as built sample, the precipitate fraction is more as comparison to contour direction. This we observe through with the help of scanning electron microscopy, and then again after heat treatment, this again go up as comparison to other samples. So this is the volume fraction which is calculated for niobium carbide samples also. So what type precipitates are there after heat treatment? So to confirm that, we can observe the microstructure of the material. So we observe the presence of gamma prime as well as gamma prime as well as gamma double prime, and some precipitates of delta phase is there. So these are the networks of delta phase, as you can see. This is the and in other samples, in hip sample, we basically saw the gamma double prime which is present in the material. So we also calculate the hardness of the sample. So we differentiate it in different parts. One is a build direction as build sample, another is hip, then hip plus heat treated. So this one we observed when we are talking about rod samples. the micro hardness of material is around to be 400, and but after heat treatment, the after deformation it went down, and then after heat treatment heat plus heat treated, the hardness of we are getting more hardness as comparison to other one. So this is like also like improve the hardness of our sample after heat treatment. So these observed in the different samples. So in this C and H is basically talking about the contour in the H direction. So overall, conclusion throughout this paper, what we observed, the contour region exhibit heterogeneity in grain morphology, because there are presence of small grains like fine grains are there. There are presence of like columnar structure is also there. Mean to say, in contour regions, heterogeneity is in the terms of like grain size is there, and no preferred texture will be there. The material is more or less random texture. But in H direction, the grain structure is uniform. Mean to say, like there are bigger sample with a high number of grain sizes there throughout your material, and other than that, those grains are strongly textured material is there. Those grains are aligned in one particular orientation, that is 100. So those are if we can say the H material is morely textured material. And then as we also calculate the precipitates in the sample, so what we observe, density of fine carbides in the contour region is more, but after heat treatment, uh, uh, there is like a the delta phase which we observe is that phase is completely dissoluted. Dissolution of the delta phase is there after heat treatment, and the presence of other gamma double prime is basically seen in that. Both as built and post treated sample, no dissimilar difference in the gamma prime and gamma double prime phase. In the content of H and contour, both are same, and after heat plus heat treated, almost same kind of hardness we observe, because the presence of gamma prime and gamma double prime both are there inside your material. So this is the first part of this is the first paper which I published in 2020 in Metrans, and then after joining here, we I work with one of the my collaborator here in Thapar, Dr. Vishal Gupta. So his student was also working on orthopedical cortical screws. So there we basically see how the fracture mechanism of 3D printed polymer based orthopedic screws is going to be different when we are changing the pattern of your material. Pattern mean to say, if we talk about manufacturing pattern, like if we talk about honeycomb structure, or if we're we are doing layering with the different patterns. So one is a honeycomb, triangle, those kind of, if we are changing this, so how it is going to be affect the mechanical behavior or microstructure behavior of polymer based screws. So first, what is cortical screw? Cortical screw is basically used for biomedical application with to join two different bones. It's having a some ASTM standards, in which the pitch of your material, like, or a screw is going to be that is around to be 1.75, and then the dia and everything is going to be same according to the ASTM standard. So this is basically CAD model of the screw which we produce, and then uh, these are the different infill patterns which we studied in this part. I'm basically focusing on the infill patterns. In this, we also studied the how the effect of scan rate is going to change the mechanical behavior, and the later part we also observe the uh, We also observe how the density of the volume fraction, density in particular, honeycomb structure is going to affect the mechanical behavior of the material. So, and then parallelly now, Dr. Vishal is again working on the like if we'll do the uh, coating on those biomedical compatible coating on this material, so how it is going to affect that mechanical behavior of material overall. So these four patterns we choose. So this is a image of FDM based additive manufacturing machine which we use to prepare these kind of material. So we choose four different infill patterns. One is triangular, honeycomb, grid, and the concentric. So then these four patterns are basically take pull out strength. Like let's suppose it's joined two different bones. So like after the part, it has a particular life. How to, like if we're taking out the or pull outing like taking out the material for screw inside your brain. So how it is going, how much strength it is going to have. So that part is also we performed. So first, the mechanical behavior, like we calculate the compressive as a tensile strength of the material. So as we can see, in if we'll talk about the compressive strength of the material, in concentric and honeycomb we get more or less same, but in tensile strength there is around to be 50 to 15 to 17% up was observed in the tensile behavior of a material. So to confirm that, first we did some microstructure analysis on those samples. So in that part, the all four samples will be taken out, because this practice is also important, because whenever like we are producing a material with the help of additive manufacturing, presence of porosities or defects will be more because of the growth and the other part. So to confirm that, because diffusion sometimes is not taking place in a proper way, then there will be chances of defects will be there or porosity will be there. To confirm that, we did some microstructure analysis of all those samples. So we observed, as comparison to other parts in consent honeycomb, there are less number of porosities are there. In concentric also, the number porosities is quite less. Porosities are quite less, but there are some places where the size of porosities is quite high. So, but in honeycomb structure, the porosity is not much. So, other than that, then the fractography of all those samples were be performed. So, what we observe, if you can see directly, there are like in this we choose two different. One is a concentric, another is a honeycomb structure. So, what we observe in both in the honeycomb structure, there is a the ductile kind of behavior, sorry, grid. In grid, these are the grid samples. So in this we observe there is a ductile kind of failure will be there. In ductile is basically whenever there is a ductile failure, it is basically cup and cone structure is there. So in this we can observe, yeah, these are the basically we are talking about the cup part. So these are the example of cup parts are there, and parallelly there are some precipitate, like some kind of precipitates or some kind of metrics of that are observed. But in honeycomb behavior, this is basically more towards a brittle failure kind of failure occurs in the sample. So this one of the key reason or one of the major reason which can because of that material having high strength as comparison to other part. So this paper was last year published in polymer composite. So in that, like we concluded that first, with the help of FDM, we it's possible to fabricate the orthopedic cortical screw. Earlier, this in normal practice, people are using mostly titanium-based screw, and those are casted only. So now we are also working on titanium-based screw to cast it with the help of SLM or some other methods of that. And there are different and with the different part, we able to do the infill patterns of grid, triangle, honeycomb, and concentric is possible with the help of different process parameters. And we observed the in cortical screws, mechanical behavior are basically changing when we are changing the infill patterns. And also, like during the publishing of this paper, one of the review we got how to check the like the density of the material, that also with the help check we checked. So that also with the confirm. And then we observe approximately 17% higher compressive strength and 30% of tensile strength we observed in honeycomb structure. The presence of fewer flaws and void justify the greater strength of the honeycomb structure, as it's revealed is a brittle kind of failure. And these lesser voids that support the mechanical strength of honeycomb materials is more as comparison to other part of the samples. So through that I end my part. So thank you for giving so much. Thank you all. So if you guys have any question, you are free.
For online participant, please ask any query.
Good afternoon, sir.
Good afternoon.
Sir, from my side, one question I just want to confirm. Sir,
Yes.
how could we measure the porosity percentage by scanning electron microscope?
On the surface, you can observe with the help of scanning electron microscopy. You can take number of images, and then there is a software called as ImageJ. Through that,
Analyze.
you can calculate the volume volume fraction of that part.
And the
Yes, sir.
percentage porosity, is it possible to calculate by image analyzer?
Uh, like yes, on the surface it is possible. The other way is the Archimedes principle you can use if there is enough porosity is there. Or nowadays, like we have other like X-ray tomography is there. So that is the best way to calculate the porosities or any defects if you have in your material.
And for defect analysis, what are the softwares used?
For defect, you can use X-ray to calculate the defect density. Those kind of structures, those kind of characterization techniques you can use. Other than that, EBSD also give you the geometry and necessary dislocations which you have in your sample. So those kind of facilities will be quite helpful if you want to calculate the defect density in your material.
Okay, sir.
So
Thank you,
there
sir.
are basically two different type of defects will be there. One is a geometric analysis dislocation. Another is a defects which you can take care of with the help of X-ray. X-ray.
Okay, sir. Thank you.
Mm.
Thank you, sir.
Any other query from the online participants? Any query from the offline participants?
No, sir. Thank you.
Please raise your hand. Okay, Dr. Hitesh, is a
Okay.
session.
Thank, thank you, sir. Thank you. Thank you.
So today is the end session for the online participant. Now for the offline, there is a lab visit. So today, this is the end session. Okay.
सर लैब विजिट कब करना है सर?